So before moving to the next example of application of local lemma, let's collect the lemma, which is called Chernoff bound. So it's about the concentration of the, some random variable, which depending on many independent random variable. So for example, if you flip a coin n times, then our intuition tells that with high probability, half n of them are head and half n of them are, tail. Not exactly half n, but close to half n. The number of heads in this trial should be somewhat close to half n with high probability. So we can actually make that more rigorous using this Chernoff bound. Suppose that x1 to xn are independent random variable such that each of them are either 0 or 1, indicate a random variable. It's 0 with probability pi, and it's a 1 with 1 minus pi for all I in bracket n. And let x be the summation of that. Then for all t between 0 and pn over 4, we have probability that it's deviate from its expectation by t is bounded by this in exponentially. So we get this upper bound, which is roughly p squared over some constant times the expectation of let's write it in the other way around. It's 1 with probability p, and it's 0 with probability 1 minus p. And expectation of x is roughly, and let's say the summation of pi over 1 over n is p. So on average, this is p, let's say. Then you get this. And then we know the expectation of x is pn. So let's consider this setup. So by the linearity of expectation, we know that the expectation is pn. And for t, which is, not too big, so it's at most 4 times the, expectation over 4. Then probability that the x is deviate from expectation by t is at most exponential in t squared over the constant times expectation of x. So this shows that if we consider the flipping coin n times, then probability that the number of head is half n times square root of, say, 100 square root of n is, you apply this, then that's the probability that x is this is almost 2 times e to the 1 million n over 2n. So you get some half million, some small number here. So with some small probability, Let's write it this way. So 1 minus some small probability, so it is concentrated in here. Anyway, so now we want to prove it. And roughly how we want to prove it is using the Markov inequality. Let's say we have some random variable y. Then we can bound the probability of y is, quite away from t, is upper bounded by the expectation of y over t, when y is non-negative random variable. However, this is not strong enough. We want to find the exponential upper bound. So instead we consider some other way. So for example, if we consider e to the y is at least e to the t, then that's the expectation of e to the y over e to the t. So, these two are actually the same event when y is non-negative. And by writing in this form, we can actually, if we somehow do the better analysis, then we can actually get a better upper bound. So what we want to do is we want to, instead of x, we want to replace it with y, and then we want to replace it with e to the some lambda y with a correct constant y. And then we want to analyze that random variable. So let yi be xi minus pi, which is yi is 1 minus pi with probability pi, and pi with probability negative pi with probability 1 minus pi. So because of this, we know that the expectation of yi is actually 0. So this is kind of normalization, so that we want to, just forget this expectation to make this 0. And let y be the summation of yi. Then it is enough to show that probability that y has absolute value bigger than or equal to t is bounded by 2 times e to the negative t square over 4pn. So again, p is this. So let lambda be a positive constant, and then we consider e to the lambda yi and e to the lambda y. So these are the random variables we want to consider. So what's the expectation of e to the lambda y? One of the other motivation of considering this exponential function, exponential of lambda y or exponential lambda yi, instead of yi itself. So if we know this expectation of e to the yi, then expectation of e to the lambda y is expectation of e to the lambda y1 plus lambda y2 plus, this is, actually the multiplication of expectation of e to the lambda yi rather than summation. So, if we somehow, bound so this kind of intuitively makes it easier to, transform each bound on each one of them into the entire, bound on the entire, this random variable in a multiplicative way. So you get a better probability estimate. So that's kind of intuition of why we consider this exponential of the random variable. Anyway, so what's this? This is that with probability pi, it has lambda to the, e to the lambda 1 minus pi. And with probability 1 minus pi, it has a value e to the negative lambda pi, which is actually e to the negative lambda pi times pi e to the lambda plus 1 minus pi. Then we can actually measure the expectation of lambda y, which is again multiplication of the expectation of e to the lambda yi. And we write this pi times e to the lambda 1 minus pi actually this is equality plus 1 minus pi, and it's e to the minus lambda pn let's just write it in one go. E to the, this is at most e to the negative lambda pn times p e lambda plus 1 minus p to the n. Why do we get this is that if we consider a function fx, which is log of x e to the lambda plus 1 minus x, then it's easy to actually check that this is concave. By concavity, we have this inequality, because average of pi is p. And you take the exponential on both sides. Then each one of these is what we get here. Once we take this out, then you get the give me a moment. Anyway, by using the concavity, we can actually prove this inequality. So, what do we have? Now we want to use the Markov to bound the probability that y is bigger than or equal to t. Then, again, this is, if you rewrite it, this is that. And that's smaller than the expectation of e to the lambda y over e to the lambda t, which is by using this inequality, you can bound this. And we put the appropriate lambda, some expression, and use some inequality. So I will not write all the calculation here. We use this inequality and then we plug that in. Then what we have is this inequality. So we get this, and then for the other direction, the probability that this is smaller than t, we also have to prove this. Similarly, we also compute this expectation. And we can actually show that this. And again, we simplify this expression and then later put lambda equal t over the np. Then with some computation, we can actually show that this holds. So by combining this, adding and this together, we can actually prove the lemma. So we get this Chernoff bound. So this shows that again, if we have an independent random variable and their summation, this summation is close to its expectation with the exponential probability, which is exponential on the measure of this, divided by the expectation of this x. Anyway, so this is one lemma that we collected. Next time we will use this together with the local lemma to prove some statement about graph